Well, this would be your statistics lifeline for Chapter 5, which is the topic of discrete random variables. Let me get this slideshow started. And we're talking about discrete random variables, which means that, first of all, the values for our variable x will be countable values. They'll be whole numbers. And they can be many different values. There can be many different values for x. And we're going to look at primarily three discrete probability distributions. One is called binomial, the second one is Poisson, the third one is hypergeometric. While we're not so concerned with the shape, but rather the probabilities for this particular chapter, I will mention that binomial distribution, when n is large, tends to look like normal distribution. The Poisson distribution is skewed to the right, and if you remember what skewed means, if it's skewed to the right, then that means there's a long tail that points off to the right side. And then hypergeometric, again, if there is a large number in the sample, then it tends to also look like a normal distribution or a bell-shaped curve. So to get us started, I've got this one example, and this example is looking at the number of households in the United States and the possible number of televisions in each one of these households. So here, from this sample of 101,501 households, there were 1,218 households with no television. Imagine. 32,379 that had one, 37,900 with two, etc. All the way up to 5. So the number of outcomes, or the possible values of x, were 0 through 5. So there's 6 possible values for x. We can calculate those probabilities just by taking the number of households with 0 and dividing by the total. And that's what's been done in each case. So for the first probability of 0.012, that was calculated using 1218 divided by 101,501, the number of households. And then each probability was calculated in the same way. And all the probabilities have to equal 1. So if you want to look at this data and see what does it tell you, first of all, we could say, well, what is the probability that a household has exactly 4 televisions? Well, that's the probability that x equals 4, meaning the number of televisions. And if we look at our table, then the probability that x is equal to 4 is 0.076, or there's a 7.6% chance that a household in the United States has 4 televisions. Okay. There's another question I'm going to ask you about this data set, and it says, what is the probability that there is at least 1 television, but no more than 3 in any given household? Now, this wording is something that is common to discrete probability distribution problems. You know, it might ask you, what is the probability of exactly 3? Or it could say at least 3 or at most 3. In this case, it's saying at least 1, but no more than 3. Well, if that's what it's asking, then it's actually asking about the probability of 1 plus the probability of 2 plus the probability of 3. We've got those 3 probabilities. So again, the probability that there's at least 1 television in a household, but no more than 3, is equal to the probability of 1 TV plus the probability of 2 plus the probability of 3, and that gives us the value of 0.884, which means there's an 88.4% chance that a given household in the United States has at least 1 but no more than 3 televisions, or you could say that they have 1, 2, or 3 televisions. So how about another example? Assume a mutual fund salesman knows that there's a 20% chance of closing a sale on each call that he or she makes. What if I wanted to know what is the probability distribution of the number of sales if he or she plans to call on 3 customers? If we let S be the probability of making a sale, then that would be 0.2. then that means that S prime, the probability of not making a sale, would be 0.8. So if this salesperson is thinking of calling on 3 customers, what is the different values that our unknown variable, random variable, could be? There's actually 4 outcomes possible in 3 sales calls. X could be 0, meaning they make no sales. They can make 1 sale, 2 sales, or 3 sales. So there's 4 possible outcomes. Now, I don't want anybody to get freaked out when you see this next table or this next slide, but this is a way that you can depict, for example, the probability when you only have a small number of trials: 1 sales call, 2 sales call, and 3 sales calls. And here's the values for X: no sales, 1 sale, 2 sale, and 3 sales. And then here's the probability of X, and this is derived all based on this distribution of the table, which is really complicated to do, or this distribution tree. But don't worry about it. You don't have to do anything like that for this class. Excel will take care of that for you. And let me skip right past that. Okay, discrete probability distributions represent a population. Absolutely. For example, there were 101,000 households that represented the data for, I'm seeing that my computer looks like it's unplugged right now, so let me put this on pause and make sure that I get that thing plugged back in. Okay, we're all plugged in, so I can continue. So what I was saying is that probability distributions, discrete probability distributions, represent populations. And just as a reminder, remember, when we're describing the population, we have what are called parameters. For example, measurements that describe the population, such as the population mean, the population variance, the population standard deviation. When we're talking about samples, then we have the sample mean, the sample variance, and the sample standard deviation. Now, the population mean, or the expected value. Here is a textbook definition. It's the weighted average of all values with weights being the probabilities. So the expected value of our random variable X is equal to mu, that's the population mean, and it's equal to the sum of X times P of X for all X, meaning the value of X times its probability for all X. So rather than look at this formula, and remember, this class, I don't want you to stress formulas or be worried about memorizing formulas. It's all about concepts. So how in the world do we determine the expected value or population mean from our random variable X? It can take on so many different values. Well, the mean for the number of for the population of the number of televisions per household. Here's our 0, or our X value, 0 through 5, our 6 different outcomes. Here's our probability for each one of those values. And all we do is sum the products. We take the probability of 0 times 0. Then you've got X equal to 1 times its probability, which would be 0.319. You've got the probability of X being 2 times its probability. And if you continue on and you do the summations, you're doing 1 times 3.192 times 0.374, 3 times 0.191, etc., you come to the expected value of X, the expected mean for the population of televisions in U.S. households, and that would be 2.084. So again, it's just a summation of all the different values of X times their probability. And in this case, that says that the mean expected number of households, average number of TVs per household in the United States is 2.084 televisions. Now, let's go back to our sales call. And I think a very important application of expected value relates to the calculation of profit. And should a business undertake maybe an investment or not? Let's say in my example here, we start out with assume the probability that an insurance agent makes a sale is 0.20. and after cost that agent earns a commission of $525. Well, if they don't make the sale, then they got to pay $75 in cost. What is their expected value from a sales call? The other question is, once you know that expected value, you have to determine, does the benefit exceed the cost, or is the opposite true? So let's take what we're given. In any of these questions, whether it's binomial, Poisson, hypergeometric, but any probability questions, you always need to take the information that's given and write it down to the side. And then from there you can formulate the problem and the calculation that you need to make. So in this case, we're going to call X is the discrete random variable of making a sales call. So X has a couple of outcomes. You can make a sale or no sale. If you make a sale, then you earn $525. If you make no sale, then you lose $75. What's the probability of making a sale? 0.2. What's the probability of not making a sale? Well, that's 0.8. How did I get that 0.8? Remember, if this is the probability of a sale, then the probability of not a sale is 1 minus the probability of a sale. In this case, it's 0.8. The probability of X column, even though there's only 2 elements in it, has to add to 1. So, what is the expected value, the mean or average value that this person can expect to make from any sales call? So we take X times P of X, and for a sale, X times P of X gives us $105. For no sale, well, they lose 60. That's $75 times 0.8. So if you add those two together, you come out with an expected or mean value per sales call of $45. Again, that's a very important application. You're going to see it. Whether it's in the book or not, you're going to see this application again. I'm sure I have it on the lab for Chapter 5. Okay, now, the 3 distributions that you need to get familiar with. Binomial. Binomial. Well, bi means 2. So a binomial experiment, in order to identify it, as it tells you here, it has a fixed number of identical trials. And that number of trials we just denote as n. Each trial has 2 possible outcomes. And those 2 possible outcomes are either success or failure. Now, those words success or failure, don't be too confused by those words. We're just going to define an event as happening as being success and not happening as being a failure. For example, success would be making a sale. Failure would be not making a sale. For all trials, the probability of success is P, and the probability of failure then is 1 minus P, and they're constant. So every time a person goes to make this sales call, he or she knows that his probability of success is 0.2. That is constant. And the last criteria is that the trials be independent, meaning if he or she goes to make a sales call at one home and is unsuccessful, that failure or lack of success or lack of making a call will not have any effect on the next call that he or she goes to make. So they're independent events. So again, I've reminded you here that labels for binomial experiment are outcomes. There's no value judgment implied when we say success. So one of the most common examples is we can flip a coin, and if we flip a coin, we can get either a head or a tail. If we would like, we could define heads as success, then that would mean tail is a failure. Other binomial examples might include an election candidate either wins or loses. An employee is a male or a female. A worker is employed or unemployed. So that would be success and failure for 3 different examples. So the binomial formula, I'm not going to even spend any time on this, but as you can see, it's pretty complicated, but we don't have to worry about it. Again, Megastat will do that for us. So I'm going to give you an example of how you would check the criteria to make sure that an experiment falls into the category of being binomial. The example here is, assume we flip a fair coin, meaning one that's not weighted in either direction. We flip it 10 times. First of all, there's a fixed number of trials, and that's n equals 10. Each trial has two possible outcomes. You're either going to get a head for success or a tail for failure. The probability of success when you toss a fair coin is 0.5. So that means the probability of failure is 0.5. The trials are independent. And as it says here, the outcome of heads on the first flip will have no impact on the subsequent coin flips. So flipping a coin 10 times is a binomial experiment because we've met all the conditions. Fixed number of trials, two possible outcomes, probability of success and failure, and independent trials. So how about another example? Now we're going to do one that relates back to that complicated tree, but we're just going to do it in a short form, and then I'll also show you how to do it in Excel, or at least another example in Excel. Okay, assume a mutual fund salesman knows that there's a 20% chance of closing a sale on each call he or she makes. We want to determine the probability of making 2 sales in 3 calls. Probability of sale is 0.8. The probability of no sale is 0.2. If we use the formula, we would get the probability of X is equal to 2, and it comes out to be 0.096, or there's about a 9.6% chance of making a sale, 2 sales in 3 calls. So I've asked you on this slide to go to Megastat, which is where I'm going to leave. So let me escape from this slideshow, and I'm going to go to Megastat. We're going to do this in Megastat, and you'll see how easy it can be to solve. So I'm in Megastat, or I'm in Excel. I click on my add-ins. I click on Megastat, and I'm looking at probability. Then I've got this list. Well, what probability is it? It's a discrete probability distribution. And now you'll notice that you've got 3 tabs: binomial, hypergeometric, and Poisson. So we're talking about binomials. The number of trials, well, the number of trials is, wasn't it 3 sales calls? 3 sales calls. The probability of success, P, well, that would be 0.2. And here is the default showing to display a graph, and I click OK, and that's it. And here comes my output. First of all, here's my number of trials, 3. My probability of success on any particular call is 0.2. And then here's the distribution of X. It can be 0, 1, 2, 3. The probability of that no sale is made is 0.512. The probability that exactly 1 sale is made is 0.3084. The probability that exactly 2 calls or 2 successes end up in a sale would be 0.096. And then the probability of 3 sales in all 3 calls is 0.00800. So you can see it's pretty remote. But anyway, there's a 10% chance in 3 sales calls that 2 will yield a sale for this mutual fund salesman. So this is our binomial distribution. You can see we got 0 has got a huge probability, 1 lower probability, 2 very low probability, and 3 barely very unlikely. As I mentioned earlier, as the number in a binomial trial rises, this distribution tends to become more normal and look like a bell-shaped curve. So anyway, that was how easy it was to do a binomial distribution. Let me return to my PowerPoints. And here is the output that we had from that particular experiment. The expected value in 3 sales call, the mean would be 0.06 or 0.06 sales in 3 calls. The variance is given and the standard deviation. We'll talk about those a bit later. Now, another question that is a binomial. Pat Statsley. Pat Statsley is a student, not a good student, taking a statistics course. Pat's exam strategy is to rely on luck for the first test. The test consists of 10 multiple choice questions. Each question has 5 possible answers, only one of which is correct. Pat plans to guess the answers to each question. So here's your question to you. What is the probability that Pat gets no answers correct? What is the probability that Pat gets 2 answers correct? Let me see if I have this on the next slide. Yeah, I do. So first of all, we got n equals 10. The probability of being correct is 1 out of 5, or 0.2. The probability of wrong then has to be 0.8. Is this a binomial experiment? Well, we got to check those 4 conditions. First of all, there is a fixed number of trials, 10. An answer can either be correct or incorrect. The probability of a correct answer doesn't change from one question to the next, and each answer is independent of the others. So if you miss the first question, that has no bearing on whether or not you're going to miss the second, third, fourth, through 10th questions. So if we were to do all of this using the formula, we would get the probability of 0 being equal to 0.1074. So let's say we did all the work, we got that answer. The probability that x equals 0, meaning that Pat gets no answers correct, is 0.1074. How would you interpret that result? Or what is the interpretation? Well, you would say the probability, or Pat has about 11% chance of getting no answers correct using the guessing strategy. Or you could say the probability is about 10.74% that he or she will get no answers correct. Now, if I went and put that into Megastat, and again, I would just go into Megastat, or add-ins, Megastat, I would go down to probability, then I would go over to binomial, or discrete probability distributions, and then select the binomial tab. And all I have to do is input 10, the number, and then the probability of success 0.2, and here's my output. So this says, the probability of getting 0 correct is 0.10737. The probability of getting exactly 1 correct is 0.26844. Probability of getting 10 correct is not going to happen. Very unlikely. The probability is 0. What's the probability of getting half of them right? Well, the probability of getting half of them right would be the probability that x equals 5. That would be 2.6 or 0.02642, which means there's about a 2.6% chance that Pat would get half of them correct. So what's the probability that Pat fails? Oh, maybe I do that on the next slide, so let me look ahead. Okay, what's the probability that Pat gets exactly 2 answers correct? Again, we can look for that in a couple of ways. In fact, let me go back to read that. Gets 2 answers correct. Okay, there's 2 ways to approach this. We can find, okay, let me go back to that previous slide since this is asking about exactly 2. Exactly 2 answers would be 0.30199, or there's about a 30% chance that Pat will get exactly 2 answers correct. Okay, we've been using binomial probability distributions to find probabilities for individual values of x. And now you're asked, find the probability that Pat fails the quiz. And that, in that case, that requires something called a cumulative probability. We want to know what is the probability that x is less than or equal to some value. So let's say that on the graded quiz, that if you get less than 50%, meaning less than 5 questions out of 10, that's considered a failed quiz. So what we want to know is we want to know what is the probability that x is less than or equal to 4. So that probability would be the probability of 0 plus 1 plus 2 plus 3 plus 4. And that comes out to be 0.9672. 0.9672. The probability of getting 4 or less answers correct is 0.9672. So it's about 97% probable that Pat will fail the test using that luck strategy and guessing at the answers. Okay, now I'm mentioning this again, you probably won't have to use it, but there is also a binomial table in the back of your book in the appendices, and I think it's the first appendix, and it's table A-1. If you were doing a binomial problem and say Megastat in your computer wasn't handy, you could look up the probabilities in a column of data in this table A1. You'd have to, for example, if you wanted to know the probability of getting 4 or less correct, then you'd have to figure out from the table each one of these individual probabilities and then add them up. But you'd still get the same result. Again, you can do that from a table. Okay, the Poisson distribution. Well, the Poisson is a little bit different, and it's kind of confusing sometimes for students, and sometimes they don't see the difference between it and binomial. First of all, it is a discrete probability distribution. Another thing that makes it different is there are no trials. The number of individual events represent successes that occur in some interval, such as a fixed period of time, a region of space, or that occur with an average rate, such as arrivals, departures, accidents, number of baskets in a quarter. What is the average in a period of time or in a period of space? So let me try to help you identify a binomial distribution question versus a Poisson distribution. Binomial has a finite number of trials, whereas Poisson may have an infinite number of trials. Success or failure in binomial is per trial or per event. Success or failure in Poisson has something to do with an interval measure. Maybe it's the success per unit of time, space, or distance. Okay, the event happens with a given probability per trial. Well, in Poisson, the average number of occurrences is constant but proportionate to the size or unit of time, space, or distance. Now, while this probably sounds a bit overwhelming, I can give you some examples to help clarify this. So, if we were talking about a Poisson distribution, then the examples could be the number of cars arriving at a service station in an hour. So in that case, the interval is the time for an hour. The number of flaws in a bolt of cloth. That relates to a specific region or a specific area being the bolt of cloth. The number of accidents in one day on a particular stretch of highway. So the interval is, as it tells you here, defined both by time, 1 day, and space, the particular stretch of highway. The number of hits on a website per minute. All of those are Poisson application. So Poisson random variable, the number of successes that occur in a period of time or an interval of space. Couple more examples. On average, 96 trucks arrive at a border crossing every hour. The number of typographical errors in a new textbook edition averages 1.5 errors per 100 pages. So, again, this is the successes. This is the interval. Again, the successes, we're calling these errors the successes. And again, 100 pages being the interval. So you've got these defining characteristics. And I'll let you go ahead and read these. But just keep in mind that Poisson relates to intervals, whether it's time, space, or region. So for Poisson, you've got this formula for x of all values. Mu is the mean number of successes in the interval. Now, even though you don't need to worry about this formula, you do need to know how to calculate the mean, meaning the number of successes in the intervals. Well, it's n times the probability of success. The unit of time or the interval should be short enough so that the mean rate is not larger than, say, a mean of or a mu of 20, less than 20. So Your book may use lambda to represent the mean number of successes in the interval. I'm not sure if yours does or not. Some do. But it's a rate, essentially a rate. So let's take and figure out how I can make a little more sense out of this. Let's go back to that example. The number of typographical errors in new editions of textbooks. Well, of course, you know it varies from book to book. But let's say that after some analysis, that a book publisher concludes that the number of errors follows a Poisson distribution, and that the number of errors in a textbook tends to be 1.5 errors per 100 pages. And then the instructor randomly selects 100 pages of a new book. What's the probability that there are no typos? Well, again, we have the luxury of going to Megastat. So all we do is go to Megastat, and let me escape out of this slideshow. Go back to Excel, and I'm going back to my first sheet, and it's blank because I really haven't input anything, and I have no data. I'm just putting it directly into Megastat. Going to select Megastat, probability, discrete probability distributions, and this time I'm going to select Poisson. Poisson, this is a fun one. All you need to put into Poisson is one value, and that's the mean rate of occurrences. So we're talking about the mean rate of occurrences in 100 pages, and that would be mean rate of errors, which would be 1.5. And then we click OK, and here comes our distribution. Poisson distribution, you can see here, tails to the right, or it's skewed to the right. And it shows you the probability, for example, of having no errors in 100 pages. 1, 2, 3, 4, 5, 6, all the way to 11. And here's our distribution table. The probability, or the values of x are random variable range in 100 pages from 0 to 12. The probability of 0 is 0.22313. And you can see all these individual probabilities. Well, what about this cumulative probability table or column? We could use that to tell us, for example, what is the probability that at most 3 errors are found in the 100 pages of a new textbook? Well, the probability that at most 3 errors would be the probability of 0, plus the probability of 1, plus the probability of 2, plus the probability of 3, which is what this number represents. 0.9436 is the cumulative probability of no errors, plus the probability of 1 error, plus the probability of 2 errors, plus the probability of 3 errors. So down here it's showing you our expected value. The mean or average number of errors we expect is 1.5. That's our rate of occurrence. And let me return back to the slideshow. Here's our distribution again. And then it asks this question. The probability of success, or what you have to remember is, the probability of success is proportional to the size of the interval. So, for example, if we wanted to know the mean value for a 400-page book, how many errors would we expect in a 400-page book? If the rate is 1.5 typos per 100 pages, then the expected value, or the mean for a 400-page book, is n times p. Well, the n is 1.5. And the P is 400 pages, not 100. So that means in 400 pages we would expect 6 errors. So remember, you do have to use that n times p, the mean, depending on what interval is asked in a question compared to the probability of success, the size of that interval. So you may need to adjust it. So for a 400-page book, what is the probability that there are no typos? Well, here it is in using the formula, but let me just skip over to Excel and do that. And again, in this case, our mean rate of occurrence is 6 errors per 400-page book. So I'm going to Excel, I'm going back to my first sheet. I'm going to go add-ins, megastat, probability, discrete probability distribution, back to Poisson, but now I've got to make a change. If the average rate of occurrences that we would expect would be 6, then that's the rate that I have to enter here. Click OK. And here we've got our distribution with a mean rate of 6. Again, the question that was asked is, if you have a 400-page book, we would expect on average 6 errors. What's the probability of 0? Well, the probability of 0 is 0.00248, which is given in this table, and it's the same thing, the same answer you would get by using the formula, which was shown on the PowerPoint slide. Okay, let me return back to that slideshow. And interpretation. Well, let's see. How would you interpret 0.002479? By the way, I wanted to mention that when you use Excel, it came out 00248. That's fine. You're going to get very, very close results. So again, what would that interpretation be? So that would be there's a 0.2% chance that you would have 0 errors in a 400-page textbook, or about 0.248% chance that there would be 0 errors in a 400-page textbook. Okay, I've referred you again in case you want to ever use it. You don't have your megastat handy. There's also Poisson tables, and in the back of your book in the appendix, it's table A2, and that can get you the same answers. So in this case, you're being asked, for a 400-page book, what is the probability that there are 5 or less typos? 5 or less typos. So x equals 5, mu is our 6 that we expect. The probability that x is less than or equal to 5, well, you could add up the probability of 0 plus 1 plus 2 plus 3 plus 4 plus 5, which would give you 0.4456. Let me go back to that spreadsheet answer. Okay, the probability of, what was it? Less than 5? Oh, I've forgotten already. I've got to go back. Hold on. Okay, probability of 5 or less. 5 or less. Okay. 5 or less. Here is the probability of from 0 to 5. So, this is the cumulative probability. 5 or less, you can take each probability, 0 through 5, add them up. And again, the answer comes out to be 4.4456, less than or equal to 5.4456. And that means there's about a 45% chance that will be 5 or less typos. Okay, hypergeometric. This is the third one. Hypergeometric, again, this one also seems very close to being binomial, but there's a big difference. In this case, we have a sample taken from a finite population, but the key is without replacement. So the probability of x, the number of successes, if it's without replacement, follows a hypergeometric distribution. So if it's without replacement, then that tells you that the trials are dependent. For both binomial and hypergeometric distributions, there's 2 possible outcomes. For this discrete random variable, you can either have success or failure. But we need to talk about, again, this without replacement. Without replacement means the probability of success is different from one trial to the next trial to the next trial. Whereas for binomial, the probability of success stays the same because each trial is independent. Whereas with hypergeometric, they are dependent. So again, for hypergeometric, the 4 characteristics, the trials are not independent. It's from a finite population. We sample without replacement, and the probability of success and failure changes from trial to trial. Wow, look at that formula. That's the formula for hypergeometric distribution for probability. for the mean and for the variance. So let me skip past that formula because you don't need to worry about it. And let me give an example here that we're going to actually throw into Excel. So it says, assume that 3 stocks are chosen randomly from a list of 10 stocks, and that of the 10 stocks, 4 stocks pays dividends. The number X of the 3 selected stocks that pay a dividend is a hypergeometric random variable. Okay, now, first of all, we've got a population here, or a sample, a list of 10 stocks. That we kind of consider our population. We're going to take a sample of 3 from that population. And what we want to know is how many of those pay a dividend, if any. So if there's 3 stocks and we're trying to find out if they pay a dividend, the possible values for X is it could be none could pay a dividend, 1 could pay a dividend, 2 could pay a dividend, and 3 could pay a dividend. And so this is, again, a hypergeometric distribution. We've got a couple of numbers in here. Actually, we've got 3 numbers, so you need to be comfortable with these. First of all, we've got 10. 10 is the number in our population. 3 is the number in the sample. And 4 is the number that pay dividends. So that's the one, the probability of success is that there's 4 possible that pay dividends. So this gets a little tricky when we go to Excel. But again, 10 is the number in the population. 3 is the number we're going to take in our sample. And 4 of the 10 have the characteristic of paying dividends. So you can denote these using capital N for 10, number in the population, N is in the sample, and R, meaning R being the rate that demonstrate that characteristic. And X, our random variable, will be the number of 3 stocks selected that pay a dividend. You're asked here on this slide to calculate the mean, variance, and probability that none of the 3 stocks pay dividends. And so let me escape from this PowerPoint slide, go to Excel, going back to Megastat, probability, discrete probability distributions. This time I'm going to select hypergeometric. The number in my population, well, there's 10 stocks I can select from. S, the number of possible occurrences. Well, there's 4 stocks in that 10 that pay dividends. And the number in my sample, I'm going to select 3 stocks from the 10. And then I'm just going to click OK. And here's my hypergeometric distribution. Again, 10 is the number in the population. 4 of those stocks exhibit the characteristic of success, which we're going to call pay dividends. And we're going to select 3 stocks in our sample. So the question that you were asked is, what is the probability that none of them pay dividends? Well, that's the probability that X equals 0. And in this case, it's 0.16667. Our expected value, that's our mean. We would expect 1.2 stocks to pay a dividend. That would be the expected value that we'd expect from a sample of 3 from 10, where 4 have the probability of success. Here's our variance, our standard deviation. Here's a graph, our bar chart showing the hypergeometric distribution with the probability of 0, 1, 2, and 3 having the characteristics. But in this particular question, you were asked, what is the probability that none pay a dividend? What is the probability that all 3 pay a dividend? Well, that would be 3 paying a dividend would be 0.033, so very slight probability. Let me return then to the slides. So that's if you did all the math and went through all those hard calculations. I'm glad we don't have to do that. So again, it's good news. You can go to Excel, Megastat, you go to probability, select discrete probability distribution, hypergeometric, and enter the required data. When doing hypergeometric, you can kind of get overwhelmed with the number of values in the question. But what you're looking for is for what value represents the population, what value represents what Megastat calls S, meaning the number of successes possible in that whole population, and then the number in the sample. Once you enter those three values and get your hypergeometric output, then you can answer the question for what is the probability of 0 through any value of x, any variable value of x. Okay, so there was my hypergeometric distribution. We've already looked at that in Megastat. And I want to give you several questions here and ask you to determine what distribution you think these questions follow. So here's the first one. Sony issued a recall for their plasma screen TVs. They choose 25 TVs and 7 do not operate. What if the inspector chooses 3 at random from 25? What is the probability that 2 of the 3 do not operate? So you're choosing between binomial, Poisson, and hypergeometric. Hopefully you've chosen hypergeometric because we just finished that one. So absolutely, this is a hypergeometric problem. If you were going to solve this in Megastat, the 25 TVs would be your capital N, the number in the population. 7 represents S, meaning out of these 25, 7 don't operate. And the sample size in this case, the small n, would be 3. So you'd enter 25 for the population, 7 for the capital S, meaning those that have the characteristic of not operating out of the 25, and then you would select 3 as the sample size. Okay, the next one. When wet water drills a well, their success rate is 0.55. Well, that's pretty good. 55% of the time they hit. And their profit is $2,550. If they do not find water, they lose $1,500. Well, that's one of those binomial experiments. And it's just like that idea that we did earlier, where you take the probability of success times the rate of profit. So it'd be 0.55 times $2,550 plus the probability of failure. Well, the probability of failure is 0.45, and you'd multiply that times a negative 1,500, and then you'd add those two calculations together to find the expected value of their endeavor. Okay, U.S. Transportation and Safety Board reports an annual average number of plane crashes is 14.6. For a given month, what is the probability that 2 crashes will occur? That 3 crashes will occur? So what distribution is this? Hopefully you realize that it's a rate and it's an interval, and we're talking about the Poisson distribution. Now, it's tricky on this one. If you were asked, for example, to solve this problem, what is the probability that 2 crashes will occur in a given month? Then you would just go to Megastat, probability, discrete distributions, and then you would select Poisson, the Poisson tab. And of course for Poisson you only have to enter one number. Now what would that number be for this problem? Well, it's the rate. So for a given month, what is the probability that 2 crashes will occur? What number are you going to enter? You don't enter 2. And you don't enter 14.6. Why? Because 14.6 represents the average annual rate of plane crashes. For this particular question, it's asking for a given month. So in order to know what the expected value based on this annual rate would be, we'd have to take this number divided by 12. And that number, 14.6 divided by 12, in fact, you don't even have to calculate it. I'm pretty sure when it comes to the rate, you can probably just input into Megastat for the Poisson tab, rate of occurrence, you can put 14.6 divided by 12 and hit OK, and Megastat will probably go ahead and calculate it. So, anyway, I hope that gives you a good idea about these different probability distributions, and that Chapter 5 goes well for you. Take care.